Hello everyone. Okay, last module, operating systems and database systems. So we'll look at operating systems first. Prepared three slide sets and all posted on Blackboard. The first set is going to introduce you to the general idea of operating systems. So I want you to understand what operating systems can do, would do, will do in the future if it is very powerful and intelligent and minimize the small in size. And then one of the hot topic in operating systems, and you've heard of that many times, maybe without understanding properly, multiprocessing and multitasking and multi-threading. Right. So the second slide gives you again a clear idea about particularly multi-threading. And then lastly, few slides for Python. So how Python can manipulate operating systems. We can manipulate operating systems in command line windows, but we can do that inside the coding. Sometimes it is very, very useful as you develop the systems. Okay. All right. So we do not have many lectures left before the end of this semester. Right? This semester, our class will end December 23rd. 2 days before Christmas holiday. I think 23rd is the last day, right?
Yeah.
23rd.
Next week we don't have class, right?
Day after Thanksgiving?
Thanksgiving.
Yeah. School closed. School closed.
So we're talking about mounting, like in the command prompt, like mounting operating systems?
That is in Linux operating systems. We do not do particularly Linux operating systems here.
Right.
But we have another course in undergraduate. Are you still undergraduate or graduate?
It's my last semester for undergraduate. So that's why I'm taking graduate classes as well. I'm doing both.
Have you taken 321?
Yeah.
Linux administration?
Yeah. Yep,
So you took?
Yeah.
You learned some from
Yeah,
that
definitely.
mount?
Definitely.
Right. And also Mac users, because the Mac is based on Linux kernel. So whenever you plugged in the extra systems and hardware, then automatically it says it is mounted, which is not the case Windows. Okay, before we get to start, although I wanted to say something about operating systems. What operating systems do you know so far?
I know of all the versions of Windows, maybe in my time, the ones that we've seen, maybe from Windows 98, possibly. Different distributions of Linux. Like
Oh,
Arch.
you do?
Yeah, some of them, like Arch, Ubuntu, Kali, was it Security Onion? That's based off Linux, right? Security Onion. All the penetration testing goes like Kali, all those. Metasploit. That's it. I don't know anything else. virtual machines. Hey, you have virtual machines
Mm-hmm.
on the operating system. I don't know. I got so far.
What about the operating systems? You have cell phone, right?
Yeah.
Smartphone.
Oh yeah, Android. We know Android.
So have you looked at the Android operating systems?
Oh, I have another one as well, and CyanogenMod, which is that's another another version of Android. It's made off, it's another phone that they have that's made.
So
off.
have you looked inside the operating systems
No.
in Android?
No.
So is like PlayStation and that stuff, is that like an operating system?
Everything inside the operating system is
Yeah,
running.
Yeah.
So he looks happy this morning. Why? It's a Friday. Every morning, are you happy?
I'm sorry, I'm like.
No, I'm not blaming you. I just described it.
Just as someone celebrates Thanksgiving Day.
Oh, that made you happy?
That made me can't sleep last night.
Oh, okay. So less sleep makes you happy the following morning? Okay, great. So I know you've heard of the operating system, names of operating systems, a bunch of those. However, how much do you know, first of all, command line, not the GUI interface. For GUI, the way that you click, small keys also can do. Even 4 years old, 5 years old toddlers, they handle almost all the graphical user interface of operating systems on tablets, right? I've seen many times. They click some and open up. Sometimes there's no way. So no go, ending the dead end, but still they can handle because it is just clickable, right? There is a graphical user interface. Let me ask you, the functionalities or capabilities provided by operating systems can be manipulated in two ways. Well, first of all, each capability, that is nothing but a program. So some developer developed it. So they call it, for example, CD, then that is change directory. So name it CD. And that in that program, that program accepts options, CD minus L, then it lists, no, not CD minus L, not CD, okay, LS, the list of the content of that directory, then LS minus L, then it lists in long format, and LS minus A, LS minus F, and all options available. So everything should be developed and saved, compiled and saved somewhere on your media. So that can be available for users to execute. So there are two ways. One way is by graphical user interface. Another way is simply executing the command. Okay? So my question to you, let's say you know everything about the graphical user interface. So you clicked every single buttons and graphical components provided by a graphical user interface. So you know everything about everything that can be handled through the graphical user interface. So you know everything about that. Question to you. Is it everything that can be provided by operating systems, or would there be some more that can be or could be or should be done in command line only? So command line user interface is bigger world than graphical user interface, although they touch the same playground. Okay. So command line is the thing that our cybersecurity majors or computer science major should know. Then graphical user interface. Right? Whatever you do, I want you to do command line. Okay. Yeah. Then, how much do you know command line Windows? Windows is good. I mean, Windows operating systems. So you can click and you can do many things very clearly and very nice to see the response from your action, response to your action. But in command line, have you tried all the graphical user interface actions in command line? Not really, right? Me neither. I didn't do that, right? Anything that you could do, the basic stuff should be done in command line. Otherwise, you may encounter a big problem when you develop something or when you install some, and when you have some issues on application programs. So from time to time, I want you to consider command line operating systems, command line execution, rather than graphical user interface. Okay, Windows, even in Windows systems. And on Mac, I want you to work on bring up terminals and work on the terminal. That is a command line user interface. Yeah. You have some comments?
Yeah, sorry, it's a question. So bringing up double terminal is Command R Enter?
Okay. On Mac, right? Yes. The first terminal, you should bring up the terminal by pressing, what is the key? Command and space bar, and there is a search window. There you type TOM, TER, then it understands quick and then open up the terminal, one terminal. Once you have one terminal, and click that window, terminal window, and then there, I think Command N, then N for new. So, you got it? Yeah. Okay. So operating systems. This is the first chapter of the book written by Silvershots, right? Silvershots and Avi Silvershots and Hank Koth, right? Avi Silvershots is in Yale right now. Yeah, both of them were in UT Austin till 20 years ago. UT Austin computer science was really good at that time, but among faculty groups there was some conflict. So many people left that department. So Silvershot's Stony Brook graduate. So he is now in Yale, and Hank Koth in Lehigh, in Pennsylvania. So this book, this is a very good book, very clear and very advanced technologies described. So this slide gives you all the issues about operating systems. So every issue, if you understand what it means, then you do not have to worry about operating systems. Once you understand the concept, then another thing is that learn command. Okay, once you learn command, those who are interested in development, then think about how you can implement the command that you can see, you can use, and the command that provided by operating systems, how you can do that on your own without using the command provided by operating systems. Can you develop it in programming? For example, Python or Java. Java is not a good language for developing command, but C. Okay. So, as you can see here, first issue is what operating systems do, and computer system organizations, computer system architecture, structure, operations. Okay. See, there are 4 issues. Organization, architecture, structure, and operations. 99.99% of operating system users are in this level, operations. Still, there's valuable. If you know how to operate operating systems properly and fully, then your life is promised. You don't have to worry about your job security. Okay? But all others, organizations, architecture, structures, needs to be considered by developer. So if you are interested in these topics, then you need to join Microsoft operating system developers. There are 2,000 developers working 30 years, but still a lot of defects. Think about it, a lot of defects. So, yeah, they developed for 30 years. I think a total 30, 40 years. Initially invented in IBM, DOS, disk operating systems. They developed about 10 years, and early late 1970s. Steve Jobs, no, not Steve Jobs, Bill Gates. Bill Gates assembled the personal computers, and then he brought back personal computers to IBM, and they negotiate. Can we run your operating systems on our personal computer? And they said, oh, by the way, we have personalized operating systems available, which is disk operating systems. So they said, okay, yeah, let's work together. That is the point Bill Gates started out. Okay, and after that, Bill Gates purchased all the license from IBM, and then they initially sold as is. That is disk operating systems. no Windows, no graphical user interface. At that time, Steve Jobs also announced Macintosh with the graphical user interface from the beginning. Okay. So to me at that time, those two systems are quite different when I was young. And then mid or late 1980s, I realized that, late 1980s, Microsoft now developed and published Windows systems, Windows operating systems. It's not called the operating systems still. I think it's a Power something. Power, yeah. And all in 1990s they have now Windows systems. That time I purchased the first my own computer.
Like a
You have
personal
to have
computer.
like a serial number to validate your operating system, right?
I don't remember, but it's a disk,
Oh,
plug disk.
Really?
Because I do not have a hard disk,
Oh wow.
only floppy. If I purchase a hard disk drive, then I have to pay $3,000. But I had only
just for that CD?
no PC,
Oh, the PC.
desktop.
Oh, I was about to say. Cool.
Desktop. I spent $1,500 to purchase my desktop. It's very heavy. No printer, no nothing, no mouse, no nothing. Okay, only big monitor. No, not big monitor. Yeah, monitor like 13-inch monitor. Monitor has very fat monitor. CRT. That's right. Cathode ray terminal. Yeah, CRT. But anyway, so Microsoft improves operating systems, but the foundation of the Microsoft operating systems is wrong. Therefore, still wrong. Wrong, I said. Wrong is. I mean, this is a terminology. From a lot of stuff. Okay, so the real concept that we need to learn is process management, memory management, storage management, and security and protection, and kernel data structures. This is very useful, but I don't think you need to know, but simply understand what kernel is. So kernel is core program sets that is common in most Linux operating systems. Android, your iPhone OS X or Mac OS, any distributions of Linux operating systems, they all have the same kernel.
BSD too.
Well, BSD, that's the first generation. And computing environment and open source operating systems. So let's see how much we could cover today. Objectives of this module is to describe basic organizations of computer systems. That's what we want to do. What is operating systems? Operating system is program sets. It's a set of programs. So each program can be executed. Okay? Not all the programs in operating systems are directly executed by human. 90% of the programs are executed by another program which is run by human. So they're all subroutine, for example, sub-programs that is supporting. They're all supporting the command line, which is useful for user to understand. Computer system structures. If you say computer, then computer is not just hardware, not just the software. So it has hardware, and if you say software, then software can be divided into two. Not just the developer's point of view, but computer organizations and computer memory management, architecture-wise, they should not be mixed. Your operating systems should reside at the designated memory space where any of your applications programs can reach. Okay, reach. If any application program can reach your operating systems, then that is the point that attacker can attack your operating systems, and therefore your operating systems will be damaged. If your operating system has damage, then your system is not anymore properly running. Sometimes it cannot be booted from the beginning, or sometimes it generates many other malwares, so your system eventually worse than a trash. Why worse than trash? Trash cannot do anything, but if your PC can do something, then it's worse than a trash. Hardware also consists of many small components. Mainly, there is a CPU and memory and I/O devices, right? Those who use these days microcontroller or small piece of gadgets and widgets, inside they have a CPU and memory. It's not RAM memory, usually EEPROM memory, very limited size. And any program and small operating systems can share together within that limited size of memory. And I/O device, many cases, like we have the PCs. PCs has USB. Microcontrollers usually have also USB outlets. Our PC has operating systems running inside the first, right? Operating systems. Operating system, that is what we want to learn here. This is a kind of software packages. Similarly, we have an application program. So we have many other courses that there you can learn how to develop applications. All right.
SDK, an SDK.
SDK, yes, software development kits. In the spring semester, if any of you are interested in iPhone app development, you can register my course. 555, you are all qualified because you finish this course 500. There you learn Objective-C, but new generations of Objective-C, which is called Swift. Those who have Mac books are highly qualified. The ideal users should have iPhone and MacBooks. But if you do not have none of those, still possible. But you have to install virtual machine on your Windows and then install Mac OS 10. Ideally, you should purchase OS 10. It's about a little bit over $200, but because this is recorded, you may get from somewhere. That's what our students did last year, last summer, right? You can install that way. You need to have Mac operating systems environment running, either on your Mac or Windows virtual machine. Emulation, Xcode, so-called, that is SDK for iPhone apps development. It has emulator, so that you can choose, for example, iPhone 6, iPhone 7.
You can like, test it on the phone, right? Oh
yeah, you can emulate it. The emulation, time for emulation, this is very fast on Mac. It's not the case, for example, Android, iPhone, Android apps development. Android apps development, there's also Android, some studio program is available, but emulation takes forever. Bring up, on Windows for iPhone, no, Android apps. I've taught Android apps development for 4 years, and then I switched to iPhone apps. So after I switched to iPhone apps, I am delighted. iPhone apps development is much simpler and nice and robust, everything. Okay. So those who do not have iPhone, Mac OS, still possible. I said still possible, but not really something that you can enjoy. But those who have MacBook, iPhone, then you can enjoy. I still have a lot of apps we developed in the class. So here. So you can develop and you can deport it on your iPhone and you can use it. Okay? So that is the application.
You said C# is now Swift. Now they're using Swift instead.
No, C# is a Microsoft product.
Okay.
It's totally different.
Oh, Objective-C.
Objective-C.
Oh, that's what you're saying.
You can learn some techniques from many courses. About how to develop application programs, right? So we have so many courses. You can learn Python, Java, C, or even web-based application programs. So PHP, JavaScript, you name it, right? But for operating systems, usually at the university level, college level, we don't touch much about operating system developments. We do a little bit of those, small pieces, right?
All right. This is an architecture in pictorial application explanation. The bottom line, we have hardware and operating systems running on top of their hardware. When you turn on, physically the switch, turn on the switch of your PC or MacBook, then your operating systems should be loaded on memory. Therefore, all the management, detailed management should be taken care of your operating systems. You don't do much because operating systems is so powerful these days. In your program, for example, in our job, Python, if you say print, then it prints on your terminal quickly, right? But if you do not have operating systems, then how can you write whatever you have on your monitor? How can you link your keyboard to the monitor? Think about that. It's not easy, right? So everything should be taken care of by operating systems. Some programs are already developed. So once you have operating systems running, then we might have multiple application programs. So one of our application program that I run now is PowerPoint slide. PowerPoint, right? PowerPoint is one of our application programs. PowerPoint is powerful. I think PowerPoint is the winner of the presentation tools. Apple also developed some presentation tool from the beginning when Microsoft announced the PowerPoint tool, which was early 1990s. I forgot the name of Apple products, similar to PowerPoints, but Apple presentation tools much nicer. It's really fancy. It rotates and we can see more like animation. But at the end, right now, PowerPoint is dominant. I don't know why. But technology-wise, Apple presentation tools much better. But I have no complaint about the PowerPoint slides. You know why?
Apple's called Keynote.
Oh yeah, Keynote. Yeah. Do you still have Keynote?
You have to buy extra.
Same thing. If you have a Mac, then you have to buy extra PowerPoint.
Yeah.
But still, you buy, right?
Keynote is more money. I think PowerPoint is free.
Yeah, it's free PowerPoint.
Is it free? No.
Yeah, it's free. I got it for
Well, I mean, your PC?
PowerPoint is free a lot of the time.
free. Yeah,
Comes
most of
with-
the time
comes
it's
with
free.
it.
You know, the PowerPoint comes with Microsoft Word,
On the Mac,
Excel.
no. Keynote is.
It's like-
Are they free? No. Oh, free on the Mac, on Mac, but not Windows.
I actually saw because PowerPoint at the office and still need to pay for Office.
Microsoft Office is not free, but PowerPoint is free.
Oh, PowerPoint PC itself is free.
Yeah, just the
Office
PowerPoint.
is Excel,
Yeah.
Word,
Access.
Access.
Yeah.
Do you pay for it?
You have to pay for that.
Is it-
For Mac users also, right?
I believe so.
So in your case, you downloaded only PowerPoint on your Mac? Oh, I see. Is it fair market?
Plus, I think Windows has more market share.
Right. Is it is a monopoly issue? Isn't there no monopoly issue?
No, I don't know.
They used to have monopoly issues a long time ago, but the current government all disappeared. But 10 or 15 years ago, there's a lot of issues. Software, monopoly issues.
Microsoft had monopoly, right?
Yeah, Microsoft has big monopoly issues. But I don't know why. Government doesn't do anything about that. For example, I used to have Windows 7 before we have Windows 10, right? Windows 7, and I have a lot of applications running on my home desktop. Keep bothering messages comes up and upgrade. But I didn't upgrade it till accidentally it activated. After that, there are so many applications that I cannot run anymore because operating system itself upgraded. I think there is a big issue, but government doesn't do anything. No control. But 15 or 20 years ago, it was a big issue. Monopoly is a big issue. It's not fair market. Okay. What operating systems do? The goal is not what, but maybe how. The goal of operating systems is to make easy interface so that casual users or uneducated users still can operate it. So currently all the Windows systems, Mac OS, reaches the goal about 90%, right? So babies can also activate some of the programs. Although they do not know the language, they still can do it. And also 80 or 90 years old grandma, grandpa, they also can do it if they intended to, right? But many cases they don't want to. But small kids, like 2 years old, 3 years old, they aggressively touch all the windows and activate the programs. When accidentally, if they link YouTube, then they are delighted. They walk everything.
I have a question. I think Windows is the only operating system that charges you money for the software. Because Linux is free.
Mac OS charges.
Mac OS is free.
No.
You just have to pay for the hardware.
No. If you want to, right, yeah.
It says
Right, yeah, in that way. But if you want to download Mac OS on your Windows systems, Windows virtual machines, then you have to pay.
You have to pay.
Yeah, I think 200 some.
Don't you need special hardware?
Right. When you purchase OS, I mean the MacBook, it comes with it.
So Mac OS X costs money too.
But Linux, free. One of the distributions of Linux is that Red Hat, but you can register, you can purchase, but it's not the price for the media, I mean operating system itself, but maintenance or technical support. If you want to receive technical support, then you need to have some contract with Red Hat. Other than that, all the Linux operating systems free. Solaris operating systems needs to be paid.
Yeah, it says here. Now Mac OS X is free now.
For any users?
Does it start with that line or is it after
It
this?
started with Mavericks.
So that
3 years ago they did free.
okay.
They used to charge money, you're right.
So in the spring, if you take my course 555, then you don't have to worry about even if you have a Windows systems. As far as you download, for example, Oracle virtual machine, that is free. But if you purchase VMware workstation, but I like VMware workstation. It is really strong and good. But it should be paid. I think about $200 or so, right? For educational purpose.
Oh, it was free.
Which one?
VMware.
VMware Play, something is free, but workstation.
What is the difference between like workstation and the player? What are those?
The other one is just lightweight.
The vSphere?
vSphere is that's a Microsoft product, right? That is also free. But
Solaris is expensive.
how much?
Up to two. Solaris 10, up to 2 sockets. 1 year, $720.
Wow.
Up to 2 sockets. And it says unlimited sockets, $1,300.
It became very cheap, 1,300.
Red Hat Enterprise Linux, $800. Or no, Red Hat Enterprise Linux unlimited sockets, $1,500.
Yeah. Solaris operating systems is really powerful and strong and secure. So any Fortune 500, the backbone, back end infrastructure is equipped with Solaris operating systems. They don't use free Linux because Linux users, Linux hackers knows everything about Linux, so they may attack. But Solaris is really powerful. Yeah, when I was in a company, then Solaris is the only operating systems.
Solaris is more safe.
Of course, it runs on Sun OS, Sun workstation. It is workstation. It's not Sun Microsystems. It's called still Sun Microsystems, right? Although it is acquired by Oracle. I'm not sure. I didn't check. But anyway, so easy to use. That is key. Another thing is good performance. Okay. So that is definition of operating systems. Operating system is a resource allocator. Operating systems is a control program. So resource allocator, therefore, it manages all the resources from CPU to the external device management, and decide between conflicting requests for efficient and fair resource use. Operating system can control the execution of programs to prevent errors and improper use of the computer. Perfectly? No, right? But try to. No universally accepted definition, but everything is a vendor chips when you order an operating system. So varies widely. This second bullet is not the case of operating systems. Each individual personal user's purpose. It's more like corporates need. the one program running at all times on the computer is called kernel. There's a core program of the operating systems. Everything else is either system program or application program. We call it system program. Again, many universities also offers the courses that can develop applications and also systems. So system development is much different from the application development. Okay, if you develop systems, then you need to touch the hardware and change hardware behaviors. In the Windows, it is called interrupt handling. All the devices that you install, for example, mouse, the mouse has the manufacturer specified interrupt handlers, so that according to that specification, the system programs needs to first to understand the manufacturer specification. Okay, many of them are standardized. For example, mouse, then it is standardized. If it is a light-driven mouse, it is a standard, or roll-based, also standard, or touchpad. Everything, not everything, almost all are standard, plus the manufacturer specific functions added. So, right. So, exactly, yeah. Driver programs can be developed also. There's a system program development, but we do not offer that course here. To develop drivers, then you have to, once you develop drivers, then you know you can improve, you can jump your programming skills from 0 to 9.5. Quick upgrade. And after that, whatever you see the device, then you can program and run it. That is a basic techniques that you can build robots. Robots is hardware, right? And you need to manipulate it in programs. There is no commercial drivers that can run robots. Well, there is some general purpose robots, right? But if you want to develop robots, then you need to develop on your own, right? Okay, there's the system programs. All right, so this is now this exciting moments. Computer startup. So far, you understand operating systems needs to be loaded. Therefore, you can activate your application program, right? Because all detailed management can be done by operating systems. So operating system is big software packages ready all the resources for your application programs to run. Number one. Number two, application programs and systems programs, operating systems programs, both are software packages. In terms of software, they are the same. They are the same programs. Operating system is also programs. Your application programs is also software programs. That's number two. Number three, any software packages, software programs cannot run if the programs are not loaded on memory first. So anything that should be loaded on your memory, then memory, don't be confused. The memory is not the storage memory. Memory is the memory on your computer. So memory sits next to CPU, so that CPU and memory can cooperate to execute your program. So in order to run the program, then you have to bring your program on the memory. We call that RAM, okay? Should be loaded on RAM first, and then your CPU control the RAM. Because operating systems and your application programs both are anyway software packages, they should be loaded before to be executed. Okay? They should be loaded. Loading programs in memory from hard disk drive, your software packages is stored on your hard disk drive. Hard disk drives can be managed by operating systems. So when you run your application program, then your application program, let me see if you have, okay, I think this is good. Okay, so in your, okay, here disk. Disk, you have your application program, okay, and also OS, operating system program. But any one of this, if it needs to be executed, it should be first loaded on memory, okay? Your app, well, before we app, what happens here is that operating systems should be loaded here. Therefore, once the operating system is loaded and controlled by CPU and managed by CPU is just processing, right? The code stores here in memory. So operating system is loaded. Once once the operating system is loaded, then after that, any application can be successfully loaded and successfully executed. There's no problem at all, right? My question here is that, who loads these operating systems initially? All other applications, programs can be loaded and managed and controlled, executed by operating systems. Without being loaded on memory, nothing can be executed. Then operating systems, all the packages in operating systems can be successfully running because it is loaded here. But the question is, initially, how operating systems can be loaded? If you turn on your computer, then operating system is not anymore here in memory. Operating systems permanently stored on your disk.
Master bootstrap.
Thank you. So we have bootstrap program. There is a bootstrap program. What is a bootstrap? James, do you have a boots? No.
Huh?
Do you have a boots?
Boots?
Yeah. You have.
Boots?
You don't have boots, right?
Sneakers.
Do you have boots? Do you wear boots?
Oh, yeah.
Cowboy boots?
No, Timberland boots.
Anybody here cowboy?
Boots.
You know cowboy, right? Cowboy boots, long boots, but back there is a bootstrap. Okay. So what bootstrap can do is that, because it's very hard to wear, right? A cowboy boots. So we have to use that bootstrap pull in so that the boots can be on your. than legs. Okay, so that's a bootstrap. Similarly, in order for initially this operating systems to be loaded, then there should be bootstrap. Bootstrap needs to be somewhere. Where is it? Bootstrap? That is on ROM. ROM? What is ROM? You know, difference between RAM and ROM, right? RAM, there's a random access memory, so power isn't needed. If there's no power, then all the content will disappear, right? What is a ROM? ROM means read-only memory, which means once it is written, then no change. Read-only. So, which means it is there all the time. So you need to have something that stays on your computer all the time that can be like a bootstrap. Okay? So mechanically, if you turn on the computer, that bootstrap runs, which is on ROM. That bootstrap brings operating systems here. Okay? Bootstrap, you can wear the boots. Once you wear the boots, then bootstrap, take hands off. Everything can be done by the boots, by the operating systems. From that point, and operating system is huge packages. So bootstrap is tiny small. So once the operating system is loaded and up and running, then this operating system can control a disk through disk controller. Disk controller is nothing but hardware and software. There's a hardware controller also. And USB controller, so hardware and software. So all hardware involved. So hardware should be controlled by driver programs, which is also part of operating systems, but many of them are added after this operating system is loaded. And some accelerator, visual accelerator. And one thing missing here is that network, right? We have also network parts. Network interface card. And through this interface card, maybe wireless or Ethernet. Ethernet, then that is IEEE 802.3. Wireless Wi-Fi, then that is IEEE 802.11. All right.
They came out with something new called EFI, Extensible Firmware Interface, which is like replacing bootstrap.
Oh, bootstrap.
It's like bootstrap loader has been replaced in computers that have extensible firmware interface, EFI.
Yeah, firmware. Yeah, it's like ROMware.
It is now part of the EFI BIOS.
It's not really software replacement, but a way of storage, storage and loading method.
It's a little faster. EFI is a little faster.
Okay, computer system operations. I/O devices and CPU can execute concurrently. What does it mean?
Same time.
What happens here is that CPU is, for example, is calculating, okay, computation. You have massive data on your disk, and you want to compute, saying, oh, I want to have some statistical analysis. Data cannot be loaded all at once on memory, RAM, because RAM is always limited in size, right? CPU is always fast. CPU runs so fast. How fast it is? How do you measure the CPU speed? Hertz, right? Gigahertz. What do you mean by gigahertz? 1 gigahertz means per second. How many instructions can be executed?
1,000 megahertz.
Giga means billion. So 1 billion instructions executed per second. That much fast. 2.12 gigahertz means 2.22 billion instructions executed. That fast.
1,000 megahertz is a gigahertz.
Mhm. So,
megahertz is a million.
mhm. No, megahertz, right. Mega means million, so billion. What about disk access time? Depending upon the disk media, right? Right now, all Mac users, you have SSD, solid state
Most of us, yeah.
right. So it runs so fast. It accesses the data so fast. But for Windows, like mine,
Rotations per minute.
this is exactly this is mechanical driver, magnetic disk
solid
drive, magnetic disk drive.
Ancient.
So there is a magnetic rotate. Some motor runs, and then there is access arm and touch the surface and identify the characters. So it takes so long. It takes so long. Before we have a multitasking, many, say 20 or 30 years ago, CPU is one at a time. CPU runs, and CPU calculates all the data currently available. Then more data needs to be read from hard drive. Then CPU is now idling, and then I/O is now accessing your disk drive and read the data and load it in memory, and therefore can be executed and computed. But now it can be done concurrently. Okay? Processing and multitasking became available. Each device controller is in charge of a particular device type. If you have a printer, then there is a printer controller. Okay, there's a hardware controller and software controller. Software controller is called driver. So you have that driver, that software, that specific software can also can only control the hardware, or other drivers cannot. So you need to have a proper, if it's not standardized, you have to have a proper driver installed and run when you access something. For example, printer. Printer is one typical, right? You need to have a specific driver. Each device controller has a local buffer. Each device. For example, again, an example of a printer, when you send the big data to be printed out, then from your CPU ship out. CPU cannot do, for example, because this is big, first half ship out, and then hold the second half and wait. Are you done? Are you done? And then send to the next. Then there is a big burden to CPU. So what happens here is that there is this specially designated space. Usually it's in RAM or hard disk drive, or even that the memory space on that hardware devices. For example, printer. Printer itself has some of the memory. Then big data can be shipped out, and that is loaded on the memory of the printer. And after that, CPU can do his own job, and the data already shipped out to the printer, and from that time, printer process should handle the data. Okay. Printer is not just a passive device these days. Printer has also computer in it. Computer in general, but more specifically, it has a processor running. Therefore, CPU, RAM, and hard disk. So hard disk holds some of the data, and hard disk also contains some data, like the logging data. So intelligent computer logged who used me, when, how much, all things can be loaded. And therefore it can be hacked, right? You can hack in the printers to print free, because it is now handled by computer. And also it is connected to the internet. So you can access remotely. CPU moves data from and to main memory, and also to and from local buffers. Right? Thing is this. This is a CPU, and let's say this is storage, hard disk. So it's a big storage. So it contains all the programs that I have, all the data that I need. Okay, and this is a CPU. So everything should be handled by this CPU. But there is a memory, this disk. So it should be loaded here first. It was here, but it should be loaded here. Therefore, I know where it is. I know all the address of my memory. So this guy knows, oh, I want to access. I want to bring that and cook and put it back. And I want to cook this and put that back there. And then there is a memory manager. Looked at all the memory space. Oh, if I do not have enough memory space, then I want to clean this up. Put it back. Swapping, right? While it's not completely done. If it is completely done, then it should be here. But it is still held by some of my program, but it's not actively Even if it is actively, if some other programs still needs some memory, then your memory manager of your operating systems should manage it, should schedule, and hey, wait a minute, go back, your home, and let me bring another here because this is urgent, so this guy will be handled. And if this is done, then swap back and bring it. Okay. So all complicated scheduling process is being done here. I/O is from the device to local buffer of controller. Device controller informs CPU that it has finished its operation by causing an interrupt. See here? Interrupt. Yeah. This is what I mean by interrupt. Anything that you need to do system programming, then you need to understand the interrupt specification and then manipulate that interrupt. That means then you can develop device drivers. That is a real developer's job. Okay. Strong computer scientists usually learn the interrupt handling. Common functions of interrupt. Interrupt transfers control to the interrupt service routine, generally through the interrupt vector, which contains the address of all the device routines, which means the device has already a bit in the program which is hardware-based runs, and manufacturers developed that. So your computer needs to control it. In the system programming, then you need to read interrupt vector specification all the time. Interrupt architecture must save the address of the interrupt instruction, and trap exception is a software generated interrupt. Exception and trap, some errors, they are all kinds of interrupt, but they are not only the interrupt. Interrupt is that when something is running, then you need to interrupt and grab the control and do some others. That is interrupt. Example for that is that you have a mouse, right? So mouse is pointing somewhere, but there should be some interrupt. Interrupt means when you move this, right? When you move your mouse from one position to another position, that movement is an interrupt. That interrupt should be handled. That should be programmed. That is an interrupt handling programming. Excited? You want to do that? We don't have such course. We do not have enough courses. To offer such courses, then what we need to do is that we need to remove all the redundant and low-level useless courses out, and then Python, one course, Java, next, data structures, next, and then all kinds of programming courses. Then we can do this interrupt and system interrupt handling and system developer programs. System here is not the system that okay. So interrupt handling is needed. So all the computer, there's interrupt handling. So look at your PowerPoint presentation here. If I press one button here on your keyboard, that is an interrupt. Okay? Should be handled. The operating system preserves the state of the CPU by storing registers and the program counter. This program counter, why program counter is needed? If interrupt comes in and if it is handled, then after the interrupt handled, then you need to go back to the previous. So you need to have some counter. Okay? Let's say 35. There is a current interrupt counting. And then there you have an interrupt. So from there you do some work. Once it is done, then you need to go back to the previous counter, 35. That is a place that you can do. What hackers can do is interrupt, and after that, after it is done, then it doesn't move back to the previous counter, but it points to somewhere there is malicious program. So after one program is done, then it's tweaked. It redirected to the returning points to somewhere where there's a malicious program running. Therefore, you said, oh, my computer is intact. After you click something. Interrupt can be identified by polling and vectored interrupt systems. Polling and interrupt, usually. What happens here is that if you have an external device, and here you have CPU, how do you know this is external mouse? How this CPU knows that you move this mouse? You move mouse, right? How my CPU identifies now you move your mouse? There are two ways. Your device interrupt, sending, hey, I'm moving. There's an interrupt. Another way is that your program keep polling. Are you moving? Are you okay? Are you okay? Because they are all connected devices. So keep polling. So two ways. Mouse is more like interrupt based. Network. Your computer is connected to the network. Ethernet, for example. Then your CPU, Ethernet cable doesn't do any interrupt. Ethernet cable does not know you have this IP address. But your CPU poll the network. Is there any message running? If there is a message running, then pull it in and check IP. If it is not, then drop. Pull it in, check. Not, then drop. Pull it in. Oh, this is a mail incoming. Okay. Plug into some mailer systems. There is polling. Okay. Network, usually polling. All other devices, from device to interrupt. So interrupted timelines here. I think we need to take a break and then speed up. All right? I think you have a broad idea of operating systems. So we'll take about 15 minutes and then restart. Okay, I/O structure. For example, input and output. If you want to send out a print job out, or if you want to receive data from external devices. They're all related with the I/O structure. So the I/O manager is available on your operating systems. So the way of receiving and sending out the data and scheduling is the issue. So all such things can be handled by operating systems. Particularly, if, for example, if your program wants to communicate, then your program itself cannot do anything with the external devices because your program does not know there is an external device currently available, right? And also your program does not check the availability or connectability, accessibility, none of those. You simply use read data from external devices. Very simple. So all details needs to be handled by operating systems, which is the system calls. So system calls, which is on your operating systems, access and make sure that if there is a external device is available, then it should tell your program, hey, it is ready. If the external device is not available as expected by your application program, then error can occur, right? We call that exception. So the system calls notify to your application program, hey, there's no device available or not found error. And all sorts of system errors from system calls is notified to your application program, then your application program may stop. Okay. So stop means your system is home. And control is still on your application program. So no other programs can grab that control and do their own jobs because currently your program is holding all the control. That is so bad, right? It happened till 20 years ago in operating systems. Right now, application program handles exceptions. So exception handler is very common in your application programs in almost all the languages. Like Java has exception handler, and Python also exception handler. So when system calls returns exceptions to your application program, then if your program is ready, for example, try an exception, okay, then if that exception occurs, then instead of hanging there and waiting forever, whatever is specified in that exception handler will be continually considered. Okay? That is our I/O structures. So, and also your CPU, speed of CPU is a lot faster than speed of I/O. So there is a I/O latency involved. But your program needs to run continually, steady and fast. So there's a controller management.
is needed. So what it does is that can there's a wait mode or restart mode. So a lot of the status dependent mode has been developed. Okay. This is storage. So that is I/O, and this is a storage. Storage can be measured in size. So in this slide, we will know what we mean by kilobytes, megabyte, gigabyte, and terabyte, and petabytes. Okay. So I want you to read this. I think many of you already know this. And storage structures. Well, actually, main memory is not storage. It's not persistent. Only temporary, while power is on. So in normal definition of storage excludes main memory. So main memory is part of processing. Instead, secondary storage, hard disk, or solid state disk, those are all storage components. Structure of storage is quite different. For example, if we have tape storage is still useful and widely used in what? Archive.
What?
Archive. If you want to archive data, the lifetime of tape is much longer than magnetic disk, much longer than solid state memory chips. So they store the data in tape for archiving purpose.
I never knew that.
You never knew that? If you go to a library, then you can check out very, very old tapes so that you can it lasts about, I think tape can last about 100 years.
Forever.
Not forever, about 100 years. But disk, CD-ROM disk, only 10 years.
Really? CD?
Yeah.
I thought it burns into the disc.
And also damage is vulnerable very easily. Tape also, if you physically scratch, then you lose. But the CD-ROM, it is partly because it is magnetic, so that effect will decay.
Yeah. Very good. CDs are magnetic.
Mm-hmm.
That's why.
And also, the more the CDs run, the quicker the lifetime will be shortened.
Anything with magnetic is decay.
Mm-hmm. Solid state disk, faster than hard disk, non-volatile, which means persistent. Various technologies and becoming more popular. One of the strengths of using SSD is the speed. It's fast.
For example, this is SSD, my external, through USB. But USB is the bottleneck. But SSD itself, storage, there's no bottleneck. So when everything that I'm working on this. I have nothing on my this. Partly because I do not trust my laptop because it has a lot of issues. So I'm only having applications software installed on this laptop. All the data here, external SSD. Storage hierarchies, speed, cost, volatility. That is, volatility is not a problem, right? For example, RAM is volatile, but it's fast.
So many stores that last forever.
Last forever?
Yeah.
We do not know yet in any experiments forever.
No, I mean like thousands of years.
Even you carve on the rock, it doesn't last 1,000 years. If you go to Rushmore Mountain, their face being damaged, and
You have very good points.
Data, DNA, blood that they're working on right now. Like, stored for a while.
So it's possible all data right now will be gone in 1,000 years.
I think that something may be developed in the future.
Yeah, internet.
Huh?
The internet, the cloud.
What do you mean by internet cloud? It is stored on SSD or
The cloud is SSD?
Yeah.
if they invest big money. Other than that, HDD,
The internet is
disk drive.
the internet is on a hard disk somewhere in the earth.
Yeah.
The only thing I can think of is keep backing up data and recycling.
We use theirs, right? Exactly, right. They swap physical storage continually, so all the storage destroyed and then put all the data, dump all the data to the new storage, and it runs continually. HDD hard disk storage, not more than 10 years. Usually, it's the same age of your PC. Don't you know that not the Mac but the Windows systems, laptop for example, with the HDD storage systems included, then if you use more than 4 or 5 years, then your storage access generates a lot of noises and eventually not only the speed, not because of the speed, but storage status reason, you cannot use it longer, right? Because the magnetic disk, it spins all the time, 24/7, for 4 years, 5 years. Then motor has damages and your surface also damages, surface of disk damages. So you do not use it longer than 4 or 5 years. I for example, desktop at home, I use very, very carefully, but it doesn't last 4 or 5 years, right? It decays. Storage device hierarchy. Bottom magnetic, and there's optical, hard disk, solid state, main memory, cache. Look at this. I want to explain here. Okay, main memory. This is your RAM. Okay, so somebody has 8 gigabytes, and all the storage here, you might have 1 terabyte. So definitely not all the data in the storage can be loaded on main memory, right? 8 gig. Although it is too big, maybe 1 terabyte main memory. For example, Google search engine since 20 years ago when they first launched search engine. So early 1990s, right? To Google. So everything, all their process, their system never need to access hard disk drive. Everything loaded on memory. So their system is so fast. Okay? So maximize the memory. So initially, at that time, 20 years ago, 1 terabyte main memory. Think about 1 terabyte main memory. It's so big.
Some memory?
Yeah,
And
1
if
terabyte.
If the service shut down, they lose everything?
No, everything is from the hard disk drive. But processing, searching, they load everything on 1 terabyte memory and search. Therefore, initially, Google search was so fast than Yahoo or any other search. Okay, initially. But anyway, there should be some bottleneck.
They still have the fastest, right?
Still fast.
Professor, what's the difference between the top of the 3 things? I mean,
Which one?
the top of these 3 things. I mean, registers.
Okay, that's what I'm trying to explain now. So you have CPU here. Okay. CPU runs everything in machine code, so-called assembler. Although you said print or assignments in very high level language, but at the low level language, everything should be controlled physical space that holds some of the data from this main memory. So register has a physical address. Okay. This is limited register. So CPU understands register 1, register 2, register 3, and so on and so forth. We have memory over there, and we have a big storage, that is hard disk drive, right? So small piece of data is loaded in our main memory, and then I have registers. So if I want to, for example, A plus B, then A comes into this register, B comes into this register, and then CPU take A and B and put it into another register C, and all the computation can be manipulated based on register. There's physical storage, physical address that is well understood by CPU. So CPU simply, hey, move this to that register, and put another register there, and things like that. All machine level manipulation can be done based upon register. That is a register. Register is the only that CPU can understand, and all the computation can be done within that register. Again, so register is nothing but CPU. Okay, almost the CPU. Memory is a little bit of storage compared to CPU. And then there is something in between. We call that cache or buffer. Cache and buffer not necessarily stores between register and memory. It can be in anywhere. Cache can be stored, sits between main memory and solid, and main memory and hard drive, main memory optical, main memory and magnetic, all, right? There we might have cache. Cache is something that, for example, if you want to cook, for your Thanksgiving dinner, then you have storage on your refrigerator. Okay, so when you cook, you need to bring something near your processor. You need to pull out something from your storage, which is a refrigerator, right? You do not grab all the time, go and open and grab one piece of small cheese and cook and open again and some others. You don't do that. You pull out lump of cheese out and close the door, and then you cut and make some process from there, right? That small space is called cache. In that way, you do not need to open up the refrigerator every single time that you need to do process. So caching important principle performed at many levels. As I said, at many levels. It's not only between register and main memory. So at any levels where there is a bottleneck. If there is a bottleneck, then we need to put cache. So that is temporarily. We put it there for improve the performance. To improve the performance only. Information in use copied from slow to faster, slow. Yeah, that is what cache can do. So definition of cache is very, very important, right? Similar to the cache on your web server, right? When you enter your login name and password, sometimes it is stored in cache. What is a cache in that case? Cache is nothing but a file, small file that contains your login name and password. So next time when you enter the same web server, then web server does not ask you to enter your login and password, but read that cache, not only login name and password, but anything that you created. For example, if you do Amazon.com shopping, then you click to something and put it into your baskets and cart, whatever, somewhere there, right? Can be stored in a cache. So next time when you enter, then bring up the cache and read the cache. Therefore, Amazon.com immediately understands what you have done so far. Okay? Again, cache is very, very efficient to continue the transaction. There is no SIM, there's no gap between the previous work and current work, right? So that is good. Efficiency and effectiveness. But it has big problem for security purpose, right? If you lose cache, you do not know whether you lose because it's still there. If it is compromised, and if that cache is nothing but file in web, but here maybe some storage, right? Some types of storage. It could be RAM, It could be real storage. Okay. If it is compromised, then your identity is lost. Direct memory access. This is it's a memory, like RAM. So, how modern computer works? See here, this in your memory, instructions and data stored in this memory, and this is your CPU, and part of this is a cache. So, data and instructions can be temporarily loaded in this cache to improve or to reduce the gap, to reduce the bottleneck between the speed of the CPU and access to time required to read something from memory, although they are very short, and although the accessing data from memory is a lot quicker than a hard disk drive somewhere here, right? But anyway, we have a cache, we have a CPU, and we have memory, and in order to load the data, depending upon the structure of this device, we can here direct memory access. And depending upon this, some storage as indirect. If it is very, very big storage, we cannot, storage address cannot be assigned, physically cannot be assigned because it is big. Then we have second layer, third layer, fourth layer. So all hierarchies within one storage device even, right? Computer system architecture, most systems use a single general purpose, multi-process and single process. So currently multi-process is very, very common. Although you have one printed chip, but it might have multiple processors printed together. It is called dual processor or quadro processor, which means physically there is one piece, but printed for more than one capabilities. If you have multiple CPUs, then you might have one memory can serve multiple CPUs. Each CPU has a register and cache. Okay. So register and cache is nothing but CPU. In this case, dual core design means you have one piece, but there you have two CPUs. Cluster systems, so multiple computer devices can cooperate together. We call that cluster. So like multiprocessor system, but multiple systems working together, usually sharing storage, and all the resources are available among themselves. Therefore, we can improve the performance. So we call that high performance computing. This cluster systems can also provide parallelization. If you have one task, one job, if that job is big, to be expected to take longer, then you need to decompose that job into multiple, and each small job can be handled by one processor efficiently, and then you distribute the small jobs to all the resources, and after they complete such small jobs, then should be collected and produce one result. This is a pictorial explanation of a cluster. operating system structures, multi-programming, time sharing, which is multitasking, and memory management. This is very, very important. In your memory, remember that anything, if needed to be executed, should be loaded on memory first. So it should be loaded in particular way that can be understood by CPU. Therefore, CPU can compute, or CPU, I mean, some program can be executed. So memory has address for simplicity. Let's say from 0 to 512 meg memory. It's a very short memory, small memory. Right? Logically, operating system stores here, and the rest you have program. Job means program. Okay, this is one program. So program 1, and another program, and another program, and another program. And also, if you have data to be used by one of the jobs, then data needs to be loaded also somewhere here within that limits. Interrupt. So we like that. I need to see where I need to stop. I think I need to stop here. Okay. Let me see. Process and memory management, storage management, message storage management. I think somehow I explained many of this. Right? This is just data structures. You don't need to consider this. Okay, what I'm going to do is I'm going to explain this kernel structure and then I'll stop for today. Okay. So kernel mode is user mode and kernel mode. It's very, very important. Operating system has a kernel. Kernel runs all the time. Kernel is a piece of operating system that should run all the time. When you execute your program, your job is nothing but your program, then along the sequence of your program logic, somewhere it should request the job to be done by operating systems, kernel, particularly if you want to access external devices or network. Not within the memory itself, but if you want to communicate outside the memory, which means your hard disk drive or printer, mouse, whatever, okay? Then when it comes to that instruction, that operating system understand what happens here. You have a program, for example, compiler or interpreter. Our Python is interpreter based, but C and Java is compiler based. Compiler, interpreter doesn't matter, but these guys understands which instructions needs system call. That is what compiler can do. Compiler is another program that compiles your application program, and it can do many things. The simple things that compiler can do is that check the grammar to see if all the instructions are properly written. Okay? And then it also checks if any instructions needs a system call, so that at that time it needs request to the kernel mode. So context needs to be switched from user mode to kernel mode along the sequence of your program. When it comes to the system calls, then control is turned over to the kernel. That is the point here. When system calls is called, then your program is not anymore under you. It is held by kernel. There's a kernel mode, which is the highest privileges here. So after executing your program, simple program, where it needs to call system calls, right after this, if you interrupt this execution, the use of that execution will be the highest privilege. That is the point that attacker can attack. That is a powerful and the most dangerous attack. If somebody attacks right here on time, say this is a time, if somebody attack and interrupt, so this execution is stopping at this point, then the owner of this process is not you, but the root administrator. But anyway, so from this point, it is executed by the kernel mode. When that system call is done, then all the control is returned to the user mode. And then from this point, that is the user's control. Okay. That's what your program is running, not only yours, all the programs. Okay. So knowing this, then you may see, oh, now I know how I can make my program more secure in this case, right? If you understand this. Any question? So now it's time to stop.
Have you heard of 30 cal exploit?
What is
30 cal exploit for Linux?
Oh,
Just came out. Google.
okay.
Just came out last month.
What is
Big
what?
exploit
Oh, is that right?
for kernel exploit.
Okay.
You get root access.
Oh yeah. If you install on your own, you have a root privileges. Okay. I will see you after Thanksgiving break. So when I see you next time, it'll be in December. Right?
Dirty copy.
Please no homework.
Dirty copy on right.
Oh, is that right? Only so we cannot get it? Then can we still download it?